Hi, my name is Brandon, and I'm here today with my co-speaker Harshal, and we're going to talk to you about a problem that would have been easy to answer 30 years ago, which is where's my workload running? And the answer would be simple. It would be, yeah, it's in the room on the 7th floor or something. But today, when asked about where my workload is, we say the cloud. With virtualization, containerization, and layers of abstraction coming into place, the answer to this is not as straightforward anymore. Where is my workload? After all, the compute has to live somewhere both logically and physically, in a country, in a room, in a server, in bare metal. But why does this matter? There are several reasons why this would matter. First, there is if our container contains confidential code, trade secrets, for example, top secret trading or military algorithms, we wouldn't want our code to be accidentally run in data centers we don't own, or even in someone's basement, for example. The second is for compliance reasons in highly regulated industries like financial, federal, and healthcare. For these industries, they go even a step further. They not only require the container workloads to be tied to a physical location, but they also want to ensure that the underlying technology stack of the machine is attested and approved. And finally, the last is for things such as export control or to enforce other legal regulation. So this is exactly the problem we're going to talk about today. How do I tie compute execution of my container to a specific location? And this is also called execution geofencing. And by the end of the talk today, we're going to learn how to do this with containers. Our claim is container image encryption plus key management equals execution geofencing, and we will show this. So to start exploring that, we're going to first look at one of the underlying technologies, which is container image encryption. So what is container image encryption? So this is an effort that started almost 2 years ago. It basically allows the ability to encrypt a container image. The process of this is fairly simple. On the left-hand side, during the build stage, we add an encrypt step, and during the runtime, we add a decrypt step. So between build and runtime, the container remains encrypted. This means that the contents of the image remains confidential over the network or even in the registry. So in a nutshell, this technology enables us to encrypt a container image so that it's only decryptable by a particular key X. And this means that we can retain the confidentiality of the image even if, for example, the registry is hacked. So this is a feature that's available today across various parts of the ecosystem like Builder, Scorpio, Containerd, cri-o, and the Docker registry. And we'll be showing some of this in the demos today. So before we go ahead, let's go through a quick asymmetric crypto primer to see how this works. So in asymmetric cryptography, such as RSA, we use key pairs made out of a public portion, which is not secret and can be published, and a private portion, which is kept secret. We can encrypt a piece of data over here on the left with a public key to get the encrypted ciphertext in writ. And then the ciphertext can then be decrypted by the private key, which only the owner has, to obtain the plain text. So now let's go through an example of encrypting image. So over here we have Alice, and we say we want to encrypt an image for Alice. So let's go through the flow here. So what Alice first has to do is to generate an RSA key pair and then publish the public portion of a key. So given the key, we can then go ahead and take our container image and encrypt it with a public key. We then take this encrypted image and push it to the registry like Docker Hub. Then finally, Alice is able to pull the encrypted image, and because only she has access to the private key and no one else, only she is able to successfully decrypt the image and run the container. So let's go ahead and take a quick look at what a demo of this looks like. So let's take a look at a demo on how we can encrypt an image for Alice. So on the left hand side here, we have Alice's workstation, which is a brown terminal. And the first step of it, as we saw earlier, is generating the keys. So we can do this by using the OpenSSL command, and we're generating our RSA key pair. So over here we have a private and public key, as we saw earlier. And what Alice has to do now is she has to make a key available so that we can encrypt an image for her. So now we have the public key, and we're going to take this public key and we're going to simulate a different workstation, and we are going to create an encrypted image so that only Alice can decrypt it with her private key. So on the right here, I'm going to copy in Alice's public key, and I'm going to paste it in here. And I'm going to build an image for Alice. So this is a really simple image. It's a busy box that just cats out. This is an encrypted image for Alice. And we are going to use the builder tool to build this image. So builder but is kind of like Docker build. It takes the Docker file and builds the image. And we are going to push this image to Docker Hub. So what we're going to do is we're going to say builder push. And we're going to add additional flag called encryption key to specify that we want to encrypt this so that it's only decryptable by Alice's private key. So we say builder push encryption key, and we have the path in Docker Hub. And we can see that it's now successfully uploaded to Docker Hub. So now that this is done, let us see whether Alice can then download and decrypt this image. So I'm just going to clear up the cache by just removing all the images currently in builder. And so what we're going to try now is we're going to say we're going to pull this image from Docker Hub. Right. So say builder pull with the image we just created. And we're going to see that it's going to try and pull the image, but it's having some trouble with it. And so in a moment, we're going to see here that it has an error that says missing private keys needed for decryption. Now, because the image was encrypted, we needed to provide a decryption key so that it can be decrypted. So in this case, we have to add an additional flag here to pass in Alice's decrypt private key. We have decryption key flag, and then we say Alice private key.pm. And what this is going to do now is it's going to successfully download and decrypt the image. We can then go ahead on Alice's workstation. We can run the image by using podman, which is kind of like Docker run. And we can see that it is running the encrypted image that we have created. All right, so in the demo, we just saw how we can create an encrypted image for Alice and how she was able to run it on her workstation. So next question Alice has is, how do I take this image and run it on my Kubernetes cluster? So let's take a look at that. So how encrypted container images work with Kubernetes cluster is through the container runtime such as cri-o and containerd. These runtimes are responsible for putting, decrypting, and unpacking the image. And in order for the runtimes to be able to decrypt the image, they, like Alice, need to have access to the key material. So today, this can be done by passing it through the file system. And for example, in cri-o, the default directory for this is etc cri-o keys. So to help distribute the key to the container runtimes more easily, we will make use of a key syncing operator that we've written. This is open source and is also available on Operator Hub. What the key syncing operator does is it allows the ability to take a Kubernetes secret as a key and distribute it to the container runtimes. So Alice can easily create a decryption key by creating a secret with the specific type equals to key. So let's take a look at this. Now we're going to show how the Alice can take the encrypted image from earlier and run it on her Kubernetes cluster. So the setup here we're using is very simple. It's a Minikube setup with the container runtime cri-o. And what we're going to do first is to install the operator that we talked about, which will synchronize the keys. So this operator is called the encryption keysync operator, and you can get it in this repository here. And so we're going to install it using Helm by first creating the namespace for it. And then we're going to use the Helm install. And so once we've successfully installed the operator here, we'll be given some instructions. But before we do anything, let's first try and run the image that we created earlier. So we're going to create a pod here, and we're going to see that it errored. So let's take a look about why it failed to run. So if we go all the way down, we can see that the error message why I could not unpack the image was because it says missing private key needed for decryption. Now this is expected because the image is encrypted and we have not yet provided the key to the container runtime to decrypt. So let's do just that. So from the instructions in the operator, we see that we can install a key by creating a secret with type key. And we're going to do exactly that. We're going to use this command and we're going to point it to the private key that we created earlier, which is in Alice's directory. Because we're decrypting, we are using the private key, and we're going to just name the secret Alice key. Cool. So once the secret has been created, let's now try and recreate the pod. So we are going to run the encrypted workload again here, and we can see that it is successfully running. And if we observe the pod, we can see that it is indeed running the image that we have created before. Awesome. So let's recap what we've kind of seen in the past two demos. So we started off by encrypting a container image that was only decryptable by Alice's private key in the first demo. And in the first demo, we saw that because Alice had her private key accessible on her local workstation, she was able to decrypt it. And therefore, the container workload that was encrypted was only decryptable on Alice's workstation because the key was only available there. So in the second example, we went ahead and Alice used the operator to make her private key accessible to the nodes in the Kubernetes cluster. So in the middle here, we see that Alice's private key is now accessible on both her workstation and Kubernetes cluster. So this meant that the container workload was now decryptable and executable on both her workstation and Alice's Kubernetes cluster. So if we take a step back, and in these scenarios, we see that Alice has been this person that has been generating the keys. She's been making them available to different entities. What Alice is essentially doing is manual key management, right? She's acting as a vault, but just a person that's generating keys and putting it in the correct locations. So if we generalize this, right, Alice's key management, what does key management do for us? So key management says that a certain key X, for example, in this case X is Alice's private key, is only accessible by a set of entities, E, where E in this case is Alice's workstation and Alice's Kubernetes cluster. So if we take the definition of container image encryption that we got from earlier, we get that container image encryption allows us to encrypt a container workload so that it's only decryptable by a particular key X. Key management says I can say a key X is only accessible by entities E. And so if we put this together, we can get the statement that says a container workload is only decryptable on the particular entities E. And this is exactly geofencing, because if entities E may be a set of workers in a particular location, that would be able to allow us to geofence the execution. Awesome. So now that we have this capability, Harshal will show you how we can use this in an enterprise scenario.
Thanks, Brandon. So now extending on what Brandon said, that you have a key management and you have image encryption. So let's get to the actual scenario where I have like a US cluster here in red and then a cluster in European Union, and I want to make sure that the container images that I'm creating are only able to run on specific cluster. For example, if I create a container image that I want to be able to make sure that it only runs on European Union cluster and nowhere else. So what we can do here is we can use image encryption and a key management in combination, such that the images will be able to run on appropriate cluster. So to elaborate the point further, if you create an image, if you encrypt the image and use the proper key management, where cluster gets authenticated, the keys are only provisioned to the cluster if it gets properly authenticated with the key management. Only in this case you can see the cluster in EU cluster, the EU cluster will get the keys, and the US cluster will not be able to get the required keys. Let's jump into demo to see this in live in action. Welcome to the demo. In this demo, we'll see how you can use image encryption to do geofencing for your container images. I have two clusters here, one running in European Union and other running in US. The one running in European Union is using container D as a CRI runtime, while one running in United States is using cri-o as its CRI runtime. Both cri-o and container D support image decryption. So let's try to build some sample workload. So I have a simple Docker file here. I just want to make sure that this sample workload only runs on the cluster that's running inside European Union. So let's build this using build-out. Once it's built, you can use the same build-out command to encrypt this image using a public key. Once it's encrypted, it can only be decrypted using this private key. So it's very important that you copy this private key to the worker nodes where you will run this image. You can manually copy this private key, or you can use this operator here, which will copy it safely to the worker nodes, and it will place it in the right location where cri-o or container D can find those keys. So now that we have built it, let's push it. And while pushing, as I mentioned, we'll use this public key to encrypt the image. Done. Good. So now that we have built it, encrypted it, and uploaded it, let's try to run this on our cluster. No access found. So I have a sample daemon set here, which will use the image that we just created here. So let's go ahead and create it. It's creating. It's running, right? That's good. So now that we are able to download the image and decrypt it and run it successfully, let's see what happens if the cluster that doesn't have this required private keys tries to run this container image. So on the US cluster, I have this, I can run the same workload, which refers to the same image that we just built here in for the European Union cluster. Let's see if we try to run it here, what happens. And you're getting an error. Let's see what this error means. So the error says that none of the private keys could be used for decryption. It means that this cluster is not able to use this image because it doesn't have the required private keys, and this is how we are able to prevent the cluster running in US from using the image that was built for running the from running the cluster that is running inside European Union. So let's try to do it other way around. So we have a Docker file here, and this is just a sample code. We want to make sure it's only able to run inside the cluster which is running in US. Let's build it using builder, and once it's built, we're gonna encrypt it using this public key, and this is the corresponding private key. I have already copied this private key on the worker nodes of this cluster so that we can successfully decrypt it. Now that I built it, let's encrypt it and push it to registry. Let me go ahead and delete the deployment that we created some time back. Not from here. And now that we have built and encrypted and pushed the image for US cluster, let's try to use it on this cluster. So I have this YAML. You can refer this. We just built this image. kubectl create -f. Get parts. It's creating. And almost there. Yes, and it's running. So now we can do the same thing that we did earlier with the image that we built for European Union cluster. What happens if the image that you just built for US cluster, if you try to use it on a cluster that's running in European Union? Let's see that. Get parts. Let me delete that. Cat USA. So this is the image that we built here. So let's go ahead and deploy it. Get parts. Get parts. It's creating. And it gives the same error that we saw here when we try to use the container image, where the required keys are not present on a cluster. That concludes my demo. Thank you.
All right, thanks, Harshal. So before we end off the talk, I'd like to address one aspect of key management that we talked about. Earlier, we said that key management allows the enforcement that key X is only accessible by particular entities E. However, today, how do we ensure that those entities can access those keys? And we today rely a lot on secure process or reliance on a trusted administrator. However, this introduces a lot of human error, and I think that this is an area that we can do a little bit better. So in research today, we are exploring how to do this to do something even more, which is to tie it to a hardware root of trust like a DPM, and even go ahead and have the ability to attest the firmware all the way up to the operating system level. So this way, not only do you have tying to a particular set of hardware, you also are able to know what is exactly running in the underlying stack of your container. So there are a couple open source technologies that do this today. There's Keylime, which is developed mainly by Red Hat, and then we have Intel Data Center Secure Libraries, also known as iSeco, which is a set of libraries that allow you to perform attestation and get attestation reports back. So in addition, there's been a publication by NIST, and this is something that we collaborated on with them. And this article talks about how you use these type of technologies together with the container platform to bootstrap trust all the way from the hardware root of trust to the containers. So this is a piece of work that is pretty interesting. In itself, it kind of is a topic in itself, so we don't have time to really go in depth. But this is something that we are constantly looking at when we'd like more people to engage on this topic. So to summarize, we talked about the question of where are my containers running. We talked about why in some scenarios this can be important and how we can achieve this through encrypted container images as well as key management. We showed you how to use encrypted container images on various components and parts of the ecosystem like Containerd, cri-o builder, and Docker distribution. And lastly, we touched a little bit on talking about highly regulated industries and high assurance. How do we kind of get to the next step in being able to bootstrap trust into our container platform? And this is something that we want to continuously work on, and we would like to be engaged with this. So we have a repository here that we've created so that people can join into the discussion. So please do feel free to come and engage with us. So that's all we had for today. Thank you very much. Quick shout out also to Stefan, Phil, who did a lot of work during the initial stages of the feature, and also with the other collaborators from OCI, Containerd, cri-o, and the containers repository. So with that, I'd like to open up to questions, and also there are links to various components that we talked about in the slides if you can download them. Thank you.
Oh, well, can you hear me? I think sorry, I was on mute. So must images be decrypted in order for static vulnerability scanners? There's a question from Casper Kramer about if you need to use the scanning tools like Trivi or Claire, do you need to decrypt? And yes, I mean, so the way it would work is you can, when you encrypt the image, you can have a multiple recipients. So let's say I encrypt the image that I need to run on my cluster, and then I can add a private key that I will associate with the a Claire, for example. So when your build pipeline, you will be able that Claire instance will be able to decrypt the image, do your scanning, and it can go ahead with that. So that way, you don't have to disclose this image to everyone except your instance where you're running the scanning. So that's question from Casper. I think you have one more question. Now, are the manifest and config files of the image also encrypted? A question from Alexandro. No, right now the first implementation we have layers of the images that are encrypted, not the manifest itself. Hey, Brandon.
Okay, cool. I'm sorry, I had some technical difficulties. So I just want to kind of add a little bit more to what Harshal said about the image scanning. So one way that he mentioned was you have a key. So something that we're looking at is you can encrypt. So there's a question in the Q&A as well on do I need to have different private keys to be able to can I use different private keys for different machines if I want to, or is an image only tied to a single private key? And the answer is you can use different private keys. You can encrypt an image for using multiple public keys. And this is kind of like an approach that we were thinking about in terms of how one would use this for a scanning service. So For example, a service like Trivy or Claire or something would expose a public key. And if you trust the service, you will encrypt your image both for your hardware as well as for the scanning services that you trust. That is one way to do it. There are a couple other approaches to do this. So what the image encryption is also done on a layer level. So what you could do is, for example, if your confidential code is only a small portion of the entire image, right? Because we serve the operating system, we serve the middleware. You could also leave your middleware operating system layers decrypted because there's no confidential material there, and only encrypt your topmost layer. So that's another way of doing it. And if you're using things like OpenSCAP or things that can scan locally, another thing that we recommend, if you're really in a high assurance scenario and you don't trust anyone, including external providers, you want to do your own scanning in-house. You could do this by doing the scanning before uploading the images to the registry.
Yep.
Yeah.
We have a question by Philip Belitz about what is the benefit of using asymmetric keys here instead of symmetric keys. So the symmetric keys are we do use symmetric keys to encrypt the layers. We just wrap them in asymmetric keys so that we can have recipients for that. So Brandon, you want to add in that?
No, I think you said it pretty well. We use both of them. We didn't go through the spec over here, but if you go to we have a couple of links in the last slide. Some of them, and if you want to download the presentation, there's a couple of links there. The spec will contain more detail about how we use both symmetric for the data, and we're using asymmetric just for the key wrapping and key delivery.
Now we know it's available in Docker Hub. There's a question whether it's available on Azure Container Registry. I haven't checked if it's available on Azure Container Registry.
I know it's available on IBM Container Registry.
Yeah, it's available on IBM Container Registry. Docker has supports it, and as soon as any other provider will upgrade to the latest version of the registry distribution, they will get the support because the code is upstream anyway.
I think we tested this with registry. If you're using Docker distribution, it's we were testing this with 2.7.1. So I think anything above 2.7 should be fine.
Yeah. I'm just going with the questions.
Okay. There's a question for Alejandro about are the manifest and config files also encrypted? So right now, only the layers are being encrypted. We had a lot of conversations about encrypting the config as well. It seems like there are some technical challenges in terms of how a lot of the tooling is written, where the code paths are not kind of similar to the layers. So we started off with layers. Configs are kind of on the roadmap. Manifest, we couldn't really figure out the use case for manifest. Config, we definitely think it should be encrypted. What the next step for this is, we're actually proposing this encryption scheme at the OCI artifacts level. So what this would mean would be you could encrypt any OCI media type, right? So you could have, if you had a manifest, you could have layers, and then if there are new OCI media types, it would just be a suffix. So if you look at the media type of the spec, if for the layers you have like tar.gzip, and what we're doing is we're just adding a plus encrypted suffix. Yep. And so what this does is it just tells it that this blob is encrypted.
That kind of answers the question Ron Chitaro has. So is there any signature details in image manifest that can be read by admission controller? If you can fetch the image and if you read the layers, the the layers will be tagged as not R or Z, it will be tagged, and then E and C will be at the end of it.
Yeah, and I would say that this will be used in tandem with any signing solutions like Docker Content Trust or Red Hat Simple Signing. Just because the encryption is already really focused on the integrity of the granular level blobs, like the layers, but in terms of like the entire manifest and the provenance, we're not really looking at that. So I would say both can be used together.
Just going over more questions.
Yeah.
Okay, looks like we're at time.
It seems like we're out of time. I guess we'll be on Slack if there are any more questions, and then we can go from there.
Yep.